Let's take a look at some of the questions on the unit for review. We're going to write for number 1 a quadratic equation with integer coefficients in standard form with the given solutions. So x is 4 or x is -3. Okay, so we'll start with factored form y equals a times x minus r1 times x minus r2, where r1 and r2 are the x-intercepts of a quadratic function. Okay, so in this case, substitute 4 for r1, so x minus 4, and then -3 for r2, so x minus -3, and simplify. Okay, at the same time, it just says, write a quadratic equation. So, and a, the leading coefficient, matters, but we can just select a equals 1, which would be the nicest quadratic function that has these x-intercepts. Okay, so it would be x minus 4, and then times x plus 3. Okay, lastly, we can distribute or FOIL, and we get x squared. It's going to be a plus 3x minus 4x, so minus x, and then -4 times 3, so minus 12. For number 2, we're going to determine the vertex axis of symmetry, whether the function opens up or down, and then we're going to rewrite it in standard form. Okay, so we'll just do one of these, part A. Okay, so we start with f of x equals negative x minus 3 squared plus 4, and we compare this to vertex form, which is y equals a times x minus x sub v squared plus y sub v. Okay, and we see that x sub v is 3 and y sub v is 4. And therefore the vertex is at 3, 4. Okay, because the leading coefficient is negative, we know that the parabola opens downward. Okay, and the axis of symmetry always passes through the vertex. And so it's a vertical line of equation x equals whatever the x coordinate of the vertex is. So in this case, 3. Okay, is the axis of symmetry. We're also asked to rewrite this in standard form. So we'll start by squaring the binomial. Okay, so that's x minus 3 squared is x squared minus 6x plus 9. And if you have a hard time doing that, just do a little bit of work on the side and write x minus 3 times x minus 3 and FOIL like we did earlier. Okay, and then plus 4. Okay, now distribute the -1. And that gives us negative x squared plus 6x minus 9. And don't forget the plus 4. And combine like terms. So negative x squared plus 6x minus 5. Okay, so if we're asked to write the equation in standard form, here it is, where a, the leading coefficient, is -1, b is 6, and c is -5. Okay, we're then going to take all of this information and try to graph the quadratic. And so the vertex was at 3, 4. The axis of symmetry was at x equals 3. Hey, we didn't say where the y-intercept is, but in standard form it's easy to tell because it's just c. And so the y-intercept is at -5. Okay, lastly, we can reflect the y-intercept across the axis of symmetry and find a corresponding point on the other side that the curve should pass through. Okay, and the parabola will look something like this. Okay, for number 3, we are given this function, f of x is x squared minus 10x plus 24. We're asked to determine the x and y-intercepts. Okay, so the y-intercept is easy because in standard form, it's just c, the constant. So y-intercept at 0, 24. Okay, the x-intercepts are not as easy. We could do it by hand, possibly, if we could factor. So x-intercepts, we're just going to do a little bit of scratch work on the side and set y equal to 0. And then see if we can put this in factored form. Okay, and so I want factors of 24 that add to give me negative 10. And so that's an x negative 6 and a negative 4. And therefore we can see what these x-intercepts are, that they're really 6 and 4. And you can go one step further, set each of the factors equal to 0. So you could set x minus 6 equal to 0 and solve, and then x minus 4 equal to 0 if you need to. Okay, so x-intercepts are at 4, so 4 comma 0, and then 6 comma 0. If you don't want to do anything by hand, that's okay. Just graph this function on your calculator and see if you can tell where the x-intercepts are, or graph in y2, put a 0, and find the intersections of the graphs. Okay, in part B, does the graph open up or down? We look at the sign of the leading coefficient, and we see the leading coefficient is a positive 1. And so therefore, this curve opens upward. And then part C, determine the coordinates of the vertex and decide whether the vertex is at a max or a min. Okay, we can use the vertex formula. X of v is equal to negative b over 2a. And b is negative 10, and a is 1. And so we end up with positive 10 over 2 times 1 over 2, which is 5. That's the x-coordinate of the vertex. And the y-coordinate of the vertex can be found by plugging the x-coordinate into the function f of x. So you're really finding f of 5. So 5 squared minus 10 times 5 plus 24, which is negative 1. And so the vertex is at 5, negative 1. Hey, we can tell whether the vertex is at a max or min by looking at the direction that the parabola opens. And because it opens upward, the vertex would be at a minimum. Okay, let's skip to number 5. Jamie throws a ball upward from the top of a building. Its height in feet over time in seconds is given by this function h of t. So what does the function tell us about the height from which the ball was thrown? So the initial height occurs when t is 0. And really what that is the h-intercept of the graph. And so we look at what the h-intercept is, which is 100. And so it was thrown initially from a height of 100 feet. Okay, when does the ball pass the top of the building on its way down? Okay, so that must be how tall the building is, 100 feet. And so we're going to set up an equation. 100 is equal to negative 16t squared plus 96t plus 100. And we want to solve this equation for t. Okay, although technically this is possible to solve by hand, you could end up factoring But why don't we go to the graph, because we'll probably need the graph to answer some of our other parts of the question. So I've entered the given function in y1 and 100 in y2. I'm going to try to graph, so zoom 6 and then zoom 0. Okay, and I want to find the intersection of the curve with this line. Notice that there are two of them, but the first one occurs at time t equals 0, which is one we already knew. So just do second trace, intersect, which is number 5. Move your cursor to the other side of the vertex, and then hit enter 3 times. Okay, so x equals 6. And that means after 6 seconds, the ball will pass the top of the building. Hey, when does the ball hit the ground? Okay, so again, it's nice to already have our graph. I'm going to just delete out y2. Maybe I'll even put a 0 in y2 because the ground is at a height of 0. Okay, and it may be hard to tell on my calculator, but we're going to find the intersection. Okay, so intersection between the curve and that line at y equals 0. And it looks like it's about 6.9 seconds. When is the ball at its highest? What is this height? Okay, so we're looking for the vertex of the parabola. And so on your calculator, you can use the max feature. So second trace, number 4, and it's kind of hard to see. I'm going to adjust my window so you can see kind of what my cursor is doing. Okay, so I'll make my Y-max bigger and hit graph. Okay, and then second trace, maximum number 4, and make sure your cursor, when it says left bound, is to the left of the maximum or the left of the vertex. Hit enter, and then scroll to the right, past the vertex, and hit enter, and then guess just to enter one more time. Okay, so the maximum occurs when t is 3, and y is, or h is 244. So when is the ball at its highest? That's after 3 seconds. And what is the height? That's the y-coordinate of the vertex, or 244 feet. In number 6, we want to find an equation of the given quadratic function. And so first thing we'll do is take a look if the vertex is kind of clearly given. And in this case, it looks like it's at -3, -3. And we can start to write the equation in vertex form as y equals a times x minus x sub v squared plus y sub v, and substitute that x and y coordinate in for x sub v and y sub v. And it becomes y is equal to a times x plus 3 squared, and then minus 3. The other thing that we need, though, is a, the leading coefficient. And so if we have another point on our curve, maybe the y-intercept, we should be able to find a. Okay, so I'll mark where the y-intercept is, and it looks like it's at 0, 6, and we'll substitute 0 for x and 6 for y. And then solve this equation for a. So 6 is equal to 3 squared, so that's 9a minus 3. Add 3 to both sides, and we have 9 equals 9a, and so a is just 1. So lastly, our equation is going to be in this form but instead of A, just put a 1. Hey, another option is to use your calculator and use the quadratic regression feature if you have 3 points on the curve. And we've labeled 2 already. So if I label one other point that's pretty clearly marked, and this would be at -6, 6, you can enter the x-coordinates in L1 and the y-coordinates in L2, and then run quadratic regression. And we'll probably do that in a little bit for another type of problem. For number 7, the cost to produce plastic toys is given by this cost function, C equals 2x plus 30, where x is the number of toys in hundreds. The total revenue from the sale of these toys is given by the function R equals -x squared plus 125x minus 1950. We want to find the break-even points, and break-even points are where the costs are equal to the revenue, or where there's just no profit. And so we can say 2x plus 30, the costs, equal the revenue, -x squared, plus 125x minus 1,950. Hey, it may be possible to factor. In order to factor, we'd have to move all terms to one side. However, it may be easier instead to just graph this system. Okay, and so in Y1, enter one of the formulas that you're given, and in Y2, enter the other. Okay, and since I'm unsure what the viewing window should be, I'm going to just try zoom 6 and then zoom 0. Okay, and then maybe zoom out some. So zoom number 3. And since I want to zoom out around this upper right-hand corner, I'm going to move my cursor to that area and then hit enter. Maybe we'll do this one more time. Okay, so it's kind of hard to tell, but if I try to find the intersection, okay, the first intersection is about when x is 19. Okay, and then do the same thing, so intersection, but move toward the other intersection, which seems like it would be over here on the right-hand side of the vertex, and then hit enter 3 times. And that's about at 103 or 104. And so rounding, we'll say that x is approximately 19. And remember that x is in hundreds. So 1900 or 1,900 or 10400 or 10,400. Okay, in part B, it says use the fact that profit is equal to revenue minus cost to find the value of x for which profit is a maximum. Okay, so we're first going to write our profit function. P equals revenue, which is -x squared, plus 125x minus 1950, and then minus cost, and that's 2x plus 30. You can simplify this or leave it if you plan on using your calculator to find the maximum or find the vertex. So I didn't simplify, I just entered this function just as I have written it, and I'm going to hit graph and see what happens. Okay, so I can see where the maximum is. I may want to zoom in, but this is not necessary. Okay, so go to second trace, maximum, which is number 4, and follow the prompts at the bottom of the screen. And so left bound, just go to the left of the maximum and hit enter. And right bound, scroll to the right of the vertex and hit enter. Okay, and then hit enter one more time. And the maximum is at when x is 61.5 and the profit is 1,802.25. Since it does say find the value of x, that is the x coordinate, and that's 61.5. Remember, that's in hundreds, or 6,150. Okay, and let's jump to number 9. A beekeeper has beehives distributed over 60 square miles of pasture land. When she places 4 hives per square mile, each hive produces about 32 pints of honey per year. For each additional hive per square mile, honey production drops by 4 pints per hive. So we want to write a function for the total production of honey in pints in terms of the number of additional hives per square mile. And so we're going to write a couple of expressions. First, one about the number of hives, and if she starts with 4 hives per square mile and adds x new hives, where x is the number of additional hives, then altogether she'd have 4 plus x hives in a square mile. Okay, but then each hive produces so much honey, so amount of honey per hive. Okay, so starts with 32 pints of honey per year. But when you add more hives, honey production for each hive drops by 4 pints per hive. So minus 4x. So altogether 32 minus 4x. Okay, so I think now we're ready to write a function for the total amount of honey based on how many additional hives added. So we're going to multiply these together, the number of hives, 4 plus x, times the amount of honey produced per hive, so 32 minus 4x. And then this one has one other piece of information, which is how many total square miles that the beekeeper has to put hives. So if it were just over 1 square mile, our function is finished. But because there's 60 of them, we're going to multiply by 60. Okay, and then how many additional hives per square mile should the beekeeper install in order to maximize honey production? So we're just going to look at this quadratic function from part A and try to find the maximum point for the vertex. So enter the function in your calculator in Y1, and we'll try zoom 6, and then zoom fit, zoom 0. Okay, and this looks good. So we're looking for the highest point of the graph. So go to second trace and maximum number 4. Okay, move your cursor to the left of the vertex and hit enter. And then move to the right of the vertex. Okay, and press enter. And then select enter one more time. Okay, so that maximum occurs when x is 2 and y is 8,640. Okay, so we need to go to the question and see which one of these values answers what we're asked to find. So how many additional hives per square mile? Okay, remember, x was the number of additional hives. So we need the x coordinate of the vertex. So we're going to just say 2. So x is 2, and that means there's 2 additional hives per square mile. Let's take a look at one more problem, number 12. A pumpkin tossing contest is held each year in Morton, Illinois, where people compete to see whose catapult will send pumpkins the farthest. One catapult launches pumpkins from 25 feet above the ground at a speed of 125 feet per second. The table shows the horizontal distances in feet the pumpkins travel when launched at different angles. So we're going to use quadratic regression to find a quadratic model that best fits the data. Okay. So the first thing that we want to do is enter our data in our lists. And so under Stat and Edit, in L1, you'll type the angles, and then in L2, we'll type the distances. Okay, then press Stat again, Calculate, and number 5 is Quadratic Regression, and hit Enter. Okay, so at this point we have A, the leading coefficient, B, the coefficient of X, and C, the constant. And we can write the equation. Okay, so I'll say this is D of X is equal to negative 0.261 X squared. Okay, I'll round to 3 places, plus 22.591X plus 23.029. And then it says, use your model to predict the distance a pumpkin would travel if launched at an angle of 67 degrees. Okay, so an angle of 67, that is an X value. We're going to find D of 67. And that's about 364.997. We'll just round to the nearest integer, so we'll say about 365 feet.